Now, if you remember, when we were trying to find the area underneath the curve when we were in rectangular form, the way we did it was we realized that we really only know the area of a rectangle. Fundamentally, that's the only area formula we all sort of know. Um, and so what we did was we said, okay, well let's break up this region into a bunch of rectangles. Right? We'll calculate. We'll get an expression at least. So etc. We'll get an expression for the area of the sum of those rectangles, and then as you let the number of rectangles go to infinity, then we see that the area under the curve gets approximated to a better and better degree as these rectangles sort of start converging toward the actual curve. So, in a nutshell, we would say, okay, if I wanted the area on the interval a to b, you break that up into a bunch of rectangles. I'm not going to draw them all. Um, and then you'd call this, I mean, ultimately, just in a nutshell, this is a small change in x, right? But we'll just in the limit as the number of rectangles goes to infinity, that becomes dx, and the height of the curve comes f of x, and of course the area ended up just being um, the definite integral, which we ended up using changing to have this better notation. So again, that's the like the height of the infinitely thin rectangle. This is the width, and so then this in total was the area of the rectangle, of the infinitely thin rectangle. Some people call that dA. So now that we are in polar curves, we're going to do a similar thing. It's just that we're going to use a different fundamental shape. A rectangle wouldn't be a good idea because the way polar graphs work is you have an angle and a distance from the pole, an r value, and if you had these sort of slanted rectangles, it's not easy or to figure out how you'd actually calculate the area of them, since if they're tilted, it's a little bit awkward, and they just don't capture area as well. The shape you end up using is actually the sector of a circle, because the sector of a circle will bend in the way we would want it to. So just as an example, let's just say this is it's a pretty crude one, but let's just break this up into a bunch of sectors of a circle, and we'll call this a change in the angle d theta, right? And let's just say this is the r value. Right, so I've got one sector, and of course what we do ultimately is we break it up into a bunch of sectors. Right, some of them will under approximate, some will over approximate. But if we can find the area, or at least an expression for the area of all of those, right, and then just let the number of sectors go to infinity, then we've essentially done the same thing we did when we did the rectangle, when we used rectangles in rectangular form, but we'll probably have a different expression. So let's just remind ourselves about what the area of a sector is. So here's a circle, right? And some proportional reasoning can tell us, well, if that's the central angle, and that's r, and I'm interested in that area, well, the area is to pi r squared. The area of the sector is to the area of the entire circle, and that should be proportional to the angle over the number of radians that a circle completes, which is 2 pi. And if you cross multiply, solve for a, you get pi r squared theta, and then divide by 2 pi, you get that the area is always 1/2 1/2 r squared theta. Right, and so that's what we're going to use. It's just that our central angle now is not a theta. We're calling our central angle there a d theta. So for us, we're going to use d theta. And so one thing I should have mentioned too is that the area is going to be from a particular angle value. So theta equals alpha to theta equals beta. So let's just say, we want the area from this angle until, the area inside this rose petal between these two angles, where that's alpha and that's beta. Well, then we're just summing up the areas of these sectors as alpha goes to, as the angle goes from alpha to beta, and the area of each sector can be described as 1/2 r squared, but again, rather than theta, the central angle we'll call d theta. And this here, of course, is the area of the sector. So now we've got a way of finding areas inside polar curves. So just to formalize, the area of a region between the origin and the curve r equals r of theta, whatever that curve may be, for theta in between alpha and beta is going to be given as this definite integral. And you could have also used, instead of r, you could use the function notation for our polar curve. Right. So now let's see how we can apply this. So this says find the area of the region in the first quadrant that is within the cardioid 1 minus cosine of theta. So that's describing this section right here. We want that area. So to do that, we're going to use our formula. So the formula says that to get that area, it's just the integral from the theta values that between which that section of the curve is traced. So you can see that that's going to be traced from 0, from theta equals 0 to theta equals pi over 2, right? Because at 0, the r value is 0, so it's at the pole, and at pi over 2, we're at 1. So that section gets traced out. If you wanted to kind of be more dynamic, it gets traced out from 0 to pi over 2. So those are the limits of integration. And then again, of course, it's 1 minus r squared, or f of theta squared, which is 1 minus cosine of theta squared d theta. Now, we could, of course, just take out our calculator and be done with it. I'm going to do this one out by hand and show you where some identities can be used to make some substitutions. So I'm going to zoom in on this because we're going to need a little bit of space. So if you expand this out, you end up getting, I'm going to take the 1/2 out, I think, 0 to pi over 2. And I'm going to expand this term here. 1 minus cosine squared becomes 1 minus 2 cosine of theta plus cosine squared of theta d theta. Now really, the antiderivative of 1 is easy. The antiderivative of negative 2 cosine of theta is not so bad. The antiderivative of cosine squared is hard. And that's when we're going to use, that's why we're going to use an identity that'll show up. So that's why I have in this note box here, I'm going to put a sort of a reminder that we have an identity that involves cosine squared that can be used to replace it. So you may recall that 2 cosine squared minus 1 is equal to, is one of the expressions equal to cosine of 2 theta. Which means that if I solve for cosine squared, it's equal to cosine of 2 theta plus 1 divided by 2. And this is actually easy to take the antiderivative of. It's easier than cosine squared. So we'll use that and make a substitution. So this is going to become 1/2 the antiderivative, the integral from 0 to pi over 2, 1 minus 2 cosine of theta, and I'm going to replace this with this cosine squared with cosine of 2 theta plus 1 divided by 2. Alright, now as crazy as it looks, it's actually not so bad. So let's just go ahead and take that antiderivative. So this is 1/2. The antiderivative of 1 is theta. The antiderivative of -2 cosine theta would be -2 sine theta. I would probably I think I'm going to view this, in fact I'm going to rewrite it, I think this will be helpful. I'm going to rewrite this as 1/2 of cosine 2 theta plus 1, because it'll just make the antiderivative easier. So that's going to be 1/2 sine of 2 theta times 1/2, right? To undo the chain rule that you'd have to do when you times by the 2, plus theta. And of course this 1/2 is stuck on the outside. So, and then we're evaluating that. This is actually another one. We're evaluating that from 0 to pi over 2. So cleaning this, it's tough to know how to clean this all up. So I think we'll clean up one more step before we evaluate. So this is 1/2 theta minus 2 sine theta. And then if you distribute this 1/2, you get 1/4 sine 2 theta plus 1/2 of theta, or theta over 2, evaluated from 0 to pi over 2. And taking up one more line, this ends up being this ends up being 1/2 pi over 2 minus 2 sine pi over 2 plus 1/4 sine of 2 times pi over 2, which is the sine of pi, plus pi over 2, which is pi over 4, minus 1/2 0 minus 2 sine of 0 plus 1/4 sine of 2 times 0, which is 0, plus 0 over 2. So I think the bottom just turns into all zeros, so we don't really need to worry about that. The top becomes, well, let's see, this becomes a 0 here, so that's gone. And so what I have left is 1/2 times pi over 2, which is pi over 4, minus 2, this is just a 1 here. So it's minus 2 times 1/2, which is just 1. So minus 1, and then 1/2 times pi over 4 is pi over 8. Plus pi over 8. And if you just combine pi over 4 and pi over 8, getting a like common denominator, that becomes 3 pi over 8 minus 1. So there's an exact value for that area of that, so that section right there. I invaded that space a little bit, but it says find the area of the entire cardioid. If you want to find the area of the entire cardioid, then you're letting theta go from 0 to 2 pi, because as it goes from 0 to 2 pi, it's going to trace this entire piece. So to do this question here, we're just evaluating the integral from 0 to 2 pi, of, again, the same expression, 1 minus cosine cosine of theta squared. D theta. We'll use the fact that we already know the antiderivative, so this is going to be 1/2 times theta minus 2 sine of theta plus 1/4 sine of 2 theta plus theta over 2, evaluated from 0 to pi, from 0 to 2 pi. And we know what happens when we plug in 0, that everything goes away, so we're just going to plug in 2 pi. So we'll get 1/2 2 pi minus sine of 2 sine of 0 is 0, plus 1/4 sine of 2 times 0 is 0. Sorry, 2 sine of 2 pi is 0, and 1/4 sine of 2 times 2 pi, or 4 pi, is 0. That's what I meant. Plus 2 pi over 2 is pi. And so you end up getting, when you distribute, you get 2 pi times 1/2 is pi, plus pi over 2, which is 3 pi over 2. So the area inside that entire cardioid or lemmason is 3 pi over 2. So even though the expression for the area inside of a polar curve is not so hard, the definite integral there, if you want to do it out by hand, you're really going to have to use one of these substitutions frequently, because when you square a trig function, which like cosine or whatnot, the cosine squareds, the sine squareds are going to require a substitution if you're going to do this out by hand. Otherwise, you just use a calculator.